Please subscribe to support the channel. For centuries, human beings have gazed at the night sky in wonder, struck by a pale, hazy band of light stretching from horizon to horizon. That glowing river of stars, the Milky Way, has inspired countless myths, stories, and questions. And yet, for all its brilliance, the Milky Way has kept one of its greatest secrets hidden from us: its true size. We've lived inside this cosmic city for as long as humanity has existed, but only now are we finally uncovering the vastness of the structure we call home. It's as though we've spent generations wandering the winding streets of an enormous metropolis without ever climbing to a high enough vantage point to see its boundaries. The Milky Way is not just a part of our sky, it is our entire galactic neighborhood, a colossal structure so immense that even the fastest thing in the universe, light itself, would take over 100,000 years to travel from one side to the other. The mystery of the Milky Way's scale has fascinated astronomers for centuries because it is not simply an intellectual exercise. It is a question about our place in the cosmos. To understand the galaxy is to understand where humanity fits in the grander scheme of the universe. Are we lost in an endless ocean of stars, or nestled comfortably within a galactic home we can measure and map? These questions carry both scientific weight and existential wonder. Every time we look up, we're staring at a part of this grand structure, yet for most of history, we had no real sense of how vast it truly was. This awe is magnified when you realize just how difficult it is to even comprehend the scale of the galaxy. Our human minds are used to thinking in terms of miles or kilometers, distances we can walk, drive, or fly. But the Milky Way forces us to think in terms of light years, the distance light travels in a single year, nearly 6 trillion miles. And the Milky Way is so big, so sprawling, that its size is measured not in tens or hundreds, but in hundreds of thousands of light years. That is almost beyond imagination. And yet, astronomers have now given us answers, through centuries of effort and with modern tools that would have seemed like magic to earlier generations. What makes this story so compelling is not just the revelation of the galaxy's true size, but the long journey humanity has taken to arrive at this knowledge. It is a tale of curiosity, persistence, mistakes, breakthroughs, and a relentless drive to know the unknown. The fact that we finally understand the Milky Way scale is a triumph of science and human determination. It is also a reminder of how small we are within the universe and yet how capable we are of unraveling its greatest mysteries. The Milky Way is not just another patch of stars scattered across the night sky. It is our cosmic address, the grand home in which our Sun, Earth, and every planet we know reside. When we look up on a clear night and see that faint, milky band stretching above us, we are actually staring at a cross-section of the galaxy itself, seen from the inside. What we perceive as a hazy glow is, in reality, the combined light of billions of distant stars, so far away that their brilliance blends together into a river of light. But that glowing band is only a fraction of what the Milky Way truly is. At its heart, the Milky Way is a vast collection of matter on a scale so immense it challenges every intuitive sense of size and distance that we carry as humans. It is made up of stars of all ages and types, nebulae where new stars are born, remnants of dead stars scattered like ashes across the sky, swirling clouds of gas and dust that stretch for light years, and something far stranger: dark matter, an invisible substance that outweighs everything we can see and yet does not emit or reflect light. This combination of luminous and invisible components forms the grand structure we call the Milky Way, a galactic ecosystem that has been evolving for billions of years. Yet, despite living inside this colossal structure, measuring it has always posed a nearly impossible challenge. Imagine trying to understand the shape and size of a forest while standing deep inside it, surrounded by trees in every direction. You can see the trees nearby, you might even detect a faint outline of hills in the distance, but you cannot rise high enough above the canopy to get the complete picture. That is exactly the challenge astronomers face when trying to determine the Milky Way's size and shape. We are embedded within it, limited to the views our vantage point allows. The problem becomes even more complex when you add interstellar dust to the equation. This dust, made of tiny particles of carbon and silicate, drifts through the galaxy like a veil, scattering and absorbing starlight. In certain directions, these clouds completely obscure what lies beyond, making the Milky Way seem patchy or incomplete when observed in visible light. To the naked eye and even early telescopes, vast portions of the galaxy are hidden, cloaked behind cosmic curtains that conceal its true scale. For centuries, This dust tricked astronomers into thinking the universe was far smaller than it really is. Another challenge is distance. On Earth, we can measure distances easily with rulers, compasses, or lasers. But in space, where distances stretch into unimaginable magnitudes, it becomes far more difficult. The nearest star system to us, Alpha Centauri, is over 4 light-years away, about 25 trillion miles. Measuring something so far requires clever methods like parallax, where astronomers track the apparent shift of stars as Earth orbits the Sun. But even this method quickly breaks down when dealing with stars thousands or tens of thousands of light-years away. For much of history, astronomers had no precise way of knowing whether a faint star was relatively close or unimaginably distant. This is why understanding the Milky Way's true size has always been one of the great challenges of astronomy. Without the ability to rise above our galaxy and look at it from the outside, we have had to piece together clues with painstaking effort. Astronomers have relied on patterns in star brightness, radio signals from interstellar gas, and eventually space-based observatories to gradually peel back the layers of mystery. Each breakthrough brought us closer, but for centuries the Milky Way remained elusive, its dimensions uncertain, its shape debated. And yet, this very difficulty adds to the wonder. Because when we finally do arrive at answers, when we can say with confidence that the Milky Way spans over 100,000 light-years, that it contains hundreds of billions of stars, and that it is enveloped in an even larger halo of dark matter, the accomplishment is staggering. It reflects not only the galaxy's immensity but also the ingenuity of human beings who, from their tiny corner of the cosmos, have managed to map out the vastness of their celestial home. The Milky Way is our cradle and our frontier. It is the stage on which every astronomical drama we can directly witness plays out. From supernova explosions to the quiet birth of new stars, from the slow swirling of spiral arms to the gravitational grip of the mysterious dark matter halo, all of it happens within this one colossal galaxy. To truly appreciate the Milky Way is to recognize that everything we know, everything we've ever seen, every sunrise and night sky, has taken place within the embrace of this galactic giant. But as majestic as the Milky Way is, the path to understanding it did not happen overnight. It was paved by centuries of thinkers, observers, and dreamers who dared to measure the immeasurable. The story of how we came to know its scale is a long one, filled with false starts, corrections, and revolutionary discoveries. It is here that history steps in, with names like William Herschel and Harlow Shapley leading the way, their early attempts to map the galaxy laying the foundation for what we know today. When we step back into history, to a time long before space telescopes and radio observatories, the Milky Way was more mystery than knowledge. For centuries, it was viewed as a celestial wonder with no clear explanation, an endless glowing river of stars arcing through the night sky. Ancient Greek philosophers like Democritus speculated that it might be made of countless distant stars, while Aristotle dismissed it as a mere atmospheric phenomenon. But as humanity's tools improved, especially with the invention of the telescope in the early 1600s, the true nature of the Milky Way slowly began to reveal itself. By the late 18th century, the great astronomer William Herschel stepped forward as one of the first to attempt a true map of our galaxy. Herschel, famed for discovering Uranus in 1781, was fascinated by the faint stars that filled the Milky Way. He and his sister Caroline spent years conducting what he called stargazing. This method involved pointing his telescope in different directions of the sky and counting the stars visible in each field of view. The logic was simple: if more stars appeared in a certain direction, then that direction must point toward a denser, deeper region of the galaxy. If fewer stars appeared, that part of the galaxy must be shallower. By systematically recording these counts across the sky, Herschel attempted to build a three-dimensional map of the Milky Way. His results were groundbreaking for the time. He concluded that the galaxy was shaped like a flattened disk, with the Sun located roughly at the center. His sketches showed a kind of squashed oval, a cosmic grindstone filled with stars, and for the first time humanity had a visual conception of the galaxy we lived in. Herschel's map was not accurate by today's standards, but it was revolutionary. It moved us beyond myth into the realm of measurable science, showing that the Milky Way was not an infinite band of light but a structured system that could, in principle, be understood. However, Herschel's method had an unavoidable flaw: it relied entirely on visible starlight. He had no way of knowing that vast clouds of interstellar dust were blocking his view of many distant stars. This dust gave the illusion that the galaxy was smaller than it truly was and made the Sun appear closer to the center than it really is. Without the ability to see beyond these obscuring clouds, Herschel's map, while visionary, painted an incomplete picture. Fast forward to the early 20th century, and another astronomer would dramatically revise our understanding, Harlow Shapley. Working at Mount Wilson Observatory in California, Shapley turned his attention not to ordinary stars but to globular clusters, dense, spherical groups of hundreds of thousands of stars orbiting the Milky Way. These clusters, because of their great luminosity and distribution, served as cosmic signposts far beyond the dusty disk of the galaxy. Shapley realized that if he could measure the distances to these globular clusters, he could determine the true scale of the Milky Way and our place within it. To do this, he used a clever method involving variable stars, specifically Cepheid variables. These stars pulsate in brightness at regular intervals, and the period of their pulsation is directly related to their intrinsic luminosity. By comparing how bright they appeared from Earth to how bright they truly were, Shapley could calculate their distances. His results were astonishing. Unlike Herschel, Shapley concluded that the Sun was not at the center of the galaxy but far from it, about 25,000 to 30,000 light-years away from the core. He showed that the globular clusters were not evenly scattered around us but concentrated toward a region in the constellation Sagittarius, which marked the true center of the Milky Way. Moreover, his calculations revealed that the Milky Way was vastly larger than anyone had imagined, on the order of 100,000 light-years across. Shapley's work was controversial at first. It shattered the long-held belief that humanity occupied the central position in the galaxy, echoing the earlier Copernican revolution where Earth was dethroned from the center of the solar system. But ultimately, his findings stood the test of time. He gave us the first reasonably accurate picture of the Milky Way's immense scale and shifted our cosmic perspective once again. It is humbling to consider what Herschel and Shapley accomplished with the tools of their time. Herschel relied on a telescope he built himself, star counts, and painstaking observation by hand. Shapley worked with early photographic plates and the mathematical relationships of variable stars. Neither had access to the advanced detectors, space observatories, or computers that modern astronomers use. Yet their pioneering efforts laid the groundwork for everything that followed. They moved humanity from the stage of wonder and myth into the era of true galactic science. What their work demonstrates is the remarkable progress of human curiosity. Each generation builds on the previous, correcting mistakes, refining measurements, and pushing the limits of knowledge. Herschel gave us the first glimpse of the galaxy's disk. Shapley revealed its vast scale and the Sun's true position. Together, they turned the Milky Way from a mystery into a measurable reality. But even then, challenges remained. How do you measure the precise size of something you cannot see from the outside? How do you deal with the problem of dust and hidden stars? These questions would occupy astronomers for decades to come, leading us directly to the next part of our story, the problem of measuring the Milky Way itself. The challenge of measuring the Milky Way can be summed up in one word: perspective. We live inside the very object we are trying to measure, and that makes the task vastly more complicated than charting a distant galaxy. When we look at Andromeda, for instance, we can see its full spiral shape against the backdrop of space. From that external vantage point, astronomers can estimate its diameter, count its spiral arms, and even detect its faint halo. But with the Milky Way, we have no such luxury. We are like ants trying to sketch the shape of a forest without ever stepping outside of the trees. Our vantage point is locked inside the disk, and that has made every attempt to measure its size a monumental challenge. One of the greatest obstacles is the vast network of interstellar dust clouds that fill the plane of the Milky Way. These are not the dust bunnies under a bed but colossal accumulations of microscopic particles of carbon, silicon, and ice that drift between stars. Though individually tiny, together they form thick, opaque curtains that block visible light. From Earth, these clouds make the Milky Way look uneven, patchy with dark rifts running across its glowing band. For centuries, these dust lanes misled astronomers, hiding the far reaches of the galaxy and making it seem far smaller than it really is. Even with Herschel's star counts or Shapley's globular clusters, large swaths of the Milky Way remained hidden behind these interstellar veils. To put the problem in perspective, in visible light, we can only see a few thousand light-years clearly in most directions. Beyond that, starlight dims and reddens, swallowed by dust. This is why for so long, estimates of the Milky Way's size varied so wildly. Some thought it was only a few thousand light-years across, while others guessed at hundreds of thousands. The dust effectively blinded us to the true extent of our galactic home. But dust is only part of the problem. Another hurdle is the sheer difficulty of measuring distances in space. On Earth, we can measure distances directly with tools, but in astronomy we must rely on indirect methods. The most fundamental of these is parallax, the apparent shift of a nearby star against the background of more distant stars as Earth orbits the Sun. The closer the star, the more it appears to shift over the course of a year. This method is elegant and precise for nearby stars, but it quickly breaks down when dealing with stars farther than a few hundred light-years away. The shifts become too small to measure with older instruments, and thus the vast majority of the Milky Way lay beyond the reach of direct parallax measurements for centuries. Without reliable distances, it was impossible to build a scale model of the galaxy. Imagine trying to map a city without knowing how far apart the streets are. You might know their directions but not their true positions. Astronomers faced this exact dilemma. They could see stars in every direction, but without knowing whether a star was close and dim or far and bright, the structure of the Milky Way was a puzzle missing most of its pieces. Even when astronomers developed new techniques, such as using Cepheid variable stars as standard candles, the problem remained complex. These methods required precise calibrations, and errors could multiply quickly. A small mistake in estimating a star's luminosity could lead to enormous errors in its distance, skewing entire maps of the galaxy. This is why different astronomers in the early 20th century often arrived at wildly different conclusions about the Milky Way's size and our place within it. And then there is the problem of perspective distortion. Because we are inside the galactic disk, the view is dominated by stars in our local neighborhood. It's like trying to gauge the size of a crowd while standing in the middle of it. Your view is filled with people nearby, while the full extent of the gathering is hidden by those around you. The stars closest to us are brightest and easiest to measure, but they are not representative of the entire galaxy. The distant spiral arms, faint outer regions, and halo structures were invisible to early observers, leaving us with an incomplete and distorted view of the Milky Way's shape. These obstacles combined to create a puzzle that resisted solution for centuries. Every time astronomers thought they had a clear picture of the Milky Way, new evidence emerged that forced them to revise their estimates. It was not until the 20th century, with advances in radio astronomy and eventually space-based telescopes, that we began to peel back the layers of dust and measure distances with far greater precision. But this struggle also illustrates something remarkable: the resilience of human inquiry. Despite being blinded by dust, trapped inside the galactic plane, and limited by the faintness of distant stars, astronomers never gave up on the quest to measure our home galaxy. Each generation found new methods to overcome the obstacles, whether it was Herschel's star gauging, Shapley's globular cluster mapping, or later radio surveys of hydrogen gas. Together, they chipped away at the problem until the picture of the Milky Way gradually came into focus. The challenges of perspective, dust, and distance have not disappeared, but today we have powerful tools that let us peer farther and with more clarity than ever before. Space telescopes can rise above the blurring atmosphere, radio waves can pierce through dust clouds, and advanced detectors can measure parallax shifts with extraordinary accuracy. With these modern instruments, we are finally beginning to grasp the full scale of the Milky Way, a breakthrough that Herschel and Shapley could only have dreamed of. The story of our understanding of the Milky Way takes a monumental leap forward when we step into the era of modern tools. For centuries, the challenges of dust, distance, and perspective kept astronomers guessing. Each generation refined the picture but never quite saw the full canvas. That changed when humanity developed the power to see the galaxy in wavelengths beyond visible light and with instruments far more sensitive than the human eye or even the best ground-based telescopes of the past. This was the beginning of a revolution that would allow us to not just estimate the Milky Way structure, but to chart it in detail, star by star, gas cloud by gas cloud, across its immense span. At the forefront of this revolution is the Gaia Space Observatory, launched by the European Space Agency in 2013. Gaia is not just another telescope. It is, in essence, the most ambitious star mapping mission ever undertaken. Its purpose is astonishingly bold: to measure the precise positions, distances, and motions of over 1 billion stars in our galaxy. To appreciate the scale of this, Remember that for most of human history, astronomers could only measure distances to a few hundred stars with any accuracy. With Gaia, we suddenly leaped to measuring billions. Gaia accomplishes this by using parallax, the same principle that ancient astronomers attempted to use but with unimaginable precision. As Earth orbits the Sun, Gaia tracks the tiny shifts in position of stars relative to more distant background objects. These shifts are often so small they are equivalent to observing a coin from thousands of kilometers away. Yet Gaia's instruments are so sensitive that it can detect these minute changes, converting them into accurate distances. This has allowed astronomers to create the most detailed three-dimensional map of the Milky Way ever constructed. But Gaia doesn't stop at distances. It also measures the motion of stars, how they move across the sky, and how fast they travel toward or away from us. This motion data, combined with distances, reveals the dynamic behavior of the galaxy. We can now trace the streaming of stars along spiral arms, detect clusters moving together through space, and even spot tidal streams of stars ripped from smaller galaxies that the Milky Way has consumed. Gaia has effectively given us the ability to watch the Milky Way in motion, not just as a static snapshot. Yet Gaia alone could not have solved all the mysteries. That's where another tool became essential: radio astronomy. Unlike visible light, radio waves can pass through interstellar dust with little obstruction. By observing the Milky Way in radio wavelengths, astronomers can peer deep into regions that visible light telescopes cannot penetrate. This has been particularly important in studying hydrogen gas, the most abundant element in the universe and the primary building block of stars. Hydrogen atoms emit a specific radio signal known as the 21-centimeter line. By mapping this signal across the sky, astronomers can trace the vast clouds of hydrogen that weave through the galaxy. These clouds outline the spiral arms, revealing the large-scale structure of the Milky Way with clarity that visible light observations could never achieve. Radio telescopes such as the Arecibo Observatory, before its collapse, the Green Bank Telescope, and arrays like the Very Large Array in New Mexico have been instrumental in creating these galactic maps. By combining Gaia's detailed star maps with radio surveys of hydrogen gas, astronomers now have a multi-layered picture of the Milky Way. It's like upgrading from a blurry sketch to a high-definition, three-dimensional model. Stars mark out the skeleton of the galaxy, hydrogen gas traces its arms, and motions reveal how it all rotates and evolves over time. These modern tools allow scientists to not only measure the Milky Way's size with greater precision, but also to uncover new structures within it that were previously invisible. Other instruments have also added to this galactic cartography. Infrared telescopes like NASA's Spitzer Space Telescope and the Wide Field Infrared Survey Explorer, WISE, have been able to peer through dust clouds, revealing stars hidden from optical view. X-ray observatories such as Chandra have exposed the energetic processes near the galactic center, including the environment around the supermassive black hole Sagittarius A. Together, these tools give us a complete, multi-wavelength portrait of our galaxy, from the coldest hydrogen clouds to the hottest regions near black holes. The result of these technological leaps is breathtaking. For the first time in human history, we are able to say not only what shape our galaxy has but also how big it is, how its stars move, and how it interacts with its neighbors. The Milky Way is no longer an abstract concept or a mysterious band of light. It is a charted territory, a colossal structure we are beginning to understand in astonishing detail. And as these tools continue to collect data, our map of the Milky Way grows more refined every year. Gaia, for instance, is still ongoing, with each new data release adding layers of precision and revealing new surprises about stellar populations, star clusters, and the motions of stars. Radio astronomy continues to probe deeper into hydrogen clouds, uncovering hidden arms and unexpected warps in the galactic disk. Together, these tools are pulling back the curtain on a galaxy that, for so long, resisted our efforts to measure it. Now that we can finally chart billions of stars and trace the outlines of spiral arms, we can begin to understand the true shape of the Milky Way itself. And here lies the next step in our journey, discovering that our galaxy is not just a simple disk of stars but a more complex structure known as a barred spiral galaxy, with arms that curl outward and a central bar that anchors its heart. When most people imagine the Milky Way, the mental picture that comes to mind is often a simple one: a flat, swirling disk of stars like a cosmic pancake. And indeed, for much of history, that was all astronomers could guess from the faint streak of light we saw overhead. But as modern tools like Gaia, radio telescopes, and infrared observatories began to peel back the layers of dust and distance, a far richer and more complex structure came into focus. The Milky Way is not just a flat disk, it is what astronomers call a barred spiral galaxy, a breathtakingly intricate system with multiple components, each playing its role in the grand architecture of our galactic home. At its core, the Milky Way is organized around a flattened rotating disk of stars, gas, and dust. This disk is about 100,000 to 120,000 light-years across, and only about 1,000 light-years thick in most places, giving it the shape of a celestial frisbee. Within this disk, the stars do not spread randomly. Instead, they cluster into long, curved structures known as spiral arms. These arms are not solid structures like the spokes of a wheel but rather regions of higher density, like cosmic traffic jams where stars, gas, and dust crowd together, lighting the galaxy in grand, sweeping arcs. The Milky Way has several major spiral arms, including the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm. Our own solar system sits within a smaller, more modest structure known as the Orion arm or Orion spur, nestled between two of the larger arms. From our vantage point inside the disk, we see these arms edge on, which is why the Milky Way appears as a dense band in the sky. If we could rise high above the galaxy and look down on it from above, we would see a graceful pinwheel of starlight sweeping outward from the center. But the disk and arms are only part of the story. At the very heart of the Milky Way lies something surprising, a stellar bar. This is a dense, elongated structure of stars that stretches across the central region of the galaxy, about 25,000 light-years long. The bar acts almost like a gravitational engine, channeling gas and stars into the core and helping to drive the spiral pattern outward. For a long time, astronomers debated whether the Milky Way had such a bar, because from our position within the disk it is hard to detect. It was only through infrared observations, which could peer through the thick dust of the galactic center, that the bar's presence was confirmed. Today, we know with confidence that the Milky Way is not just a spiral galaxy but a barred spiral galaxy, much like 2/3 of spiral galaxies in the universe. Beyond the bar and spiral arms, the Milky Way structure includes several other fascinating layers. Surrounding the disk is the galactic bulge, a roughly spherical swarm of older stars that form a central hub. This bulge is densely packed, with stars orbiting in complex patterns rather than in the neat, flat orbits of the disk. The bulge itself is slightly elongated, blending into the stellar bar at its core. And then, extending far beyond the visible disk, we find the galactic halo. This halo is a vast, diffuse sphere of ancient stars, globular clusters, and, most significantly, dark matter. It stretches hundreds of thousands of light-years outward, dwarfing the visible galaxy. Though faint and difficult to observe directly, the halo plays a critical role in holding the Milky Way together, its dark matter exerting the gravitational force that keeps the outer stars from flying away as the galaxy rotates. To truly grasp the Milky Way's shape, it helps to imagine it in layers. At the smallest scale is the galactic center, anchored by a supermassive black hole. Around it stretches the bar and bulge, then the thin, bright disk with its spiral arms, and finally the vast, faint halo that envelops it all. Each layer is interconnected, each contributing to the grand structure we call home. What makes this discovery even more remarkable is how hard-won it has been. From inside the disk, we cannot simply look down and see the bar and spiral arms laid out before us. Instead, astronomers have pieced the picture together like a cosmic puzzle, using star counts from Gaia, gas maps from radio astronomy, infrared surveys of the bulge, and the motions of globular clusters in the halo. The result is a detailed model that finally reveals the Milky Way's true form, a barred spiral galaxy with a diameter of about 100,000 to 120,000 light-years, its arms winding gracefully outward like the arms of a vast stellar pinwheel. And yet, even now, surprises continue to emerge. Studies show that the disk of the Milky Way is not perfectly flat but slightly warped and twisted at the edges, like a vinyl record left in the sun. This warp may be the result of gravitational interactions with smaller galaxies orbiting us or the uneven distribution of dark matter in the halo. Such features remind us that the Milky Way is not a static object but a living, evolving system, shaped by billions of years of cosmic history. Understanding the galactic shape gives us more than just a sense of cosmic geometry. It provides the framework for everything else we know about our home. It helps us understand where stars are born, how they move, and how the galaxy recycles its gas and dust over time. It even allows us to predict how the Milky Way will evolve in the future, when its spiral arms and bar may transform under the gravitational influence of nearby galaxies. Now that we know the Milky Way's true form, we can begin to ask deeper questions about what fills it. The galaxy is not just a structure of arms and bars but a vast population of stars of every kind, young and old, massive and small, each tracing out the spiral arms in their own way. These stellar populations are the next layer of the story, helping us not only map the galaxy but also understand its history and evolution. The Milky Way is more than just a shape of arms, bars, and halos. It is a vibrant, living ecosystem made up of hundreds of billions of stars. And not all stars are the same. They come in different ages, sizes, colors, and stages of life. This diversity isn't just a matter of cosmic beauty. It is essential for understanding and mapping the galaxy itself. In fact, it is the stellar population of the Milky Way that has allowed astronomers to trace its spiral arms, reveal its history, and even estimate its true size. Every star is like a breadcrumb scattered across the galaxy, and by following them, we can outline the vast contours of our home. Let's start with the youngest and most massive stars. These stellar giants, often many times the mass of our Sun, burn brightly and live fast, exhausting their nuclear fuel in just a few million years, a blink of an eye compared to the billions of years many stars endure. Because of their short lifespans, these stars do not have time to wander far from where they were born. They remain clustered within the spiral arms, nestled in the same giant molecular clouds that gave them life. Their intense radiation illuminates the gas around them, creating bright regions of glowing hydrogen known as H2 regions, which act as neon signs marking the galaxy's arms. Astronomers use these hot, blue, short-lived stars as tracers for spiral structure, since their presence pinpoints the very sites where new stars are being forged. On the other end of the spectrum are the oldest stars. These stars, often small and dim red dwarfs or ancient remnants of earlier generations, can be found throughout the galaxy. Many are concentrated in the halo or the central bulge, forming some of the oldest stellar populations we know. Globular clusters, for instance, contain stars that are more than 12 billion years old, nearly as old as the galaxy itself. These ancient stars serve as time capsules, preserving clues about the Milky Way's early history and how it assembled from smaller protogalaxies long ago. They don't trace spiral arms, but they provide critical information about the galaxy's earliest chapters, helping astronomers reconstruct how the Milky Way grew to its present size. Between these extremes lies a vast variety of stars like our own Sun, middle-aged, relatively stable, and distributed widely across the galactic disk. These stars live for billions of years, so they have more time to drift away from their birthplaces. They do not mark spiral arms as clearly as massive young stars, but they provide an invaluable bridge between stellar generations. By studying their motions, astronomers can map how the disk rotates, revealing the gravitational pull of both visible matter and the hidden dark matter that shapes the galaxy's dynamics. One of the most powerful techniques astronomers use involves variable stars, particularly Cepheid variables and RR Lyrae stars. Cepheids, as mentioned earlier, are young, luminous stars that pulse in brightness with a period directly related to their intrinsic luminosity. By comparing their actual brightness to their observed brightness, astronomers can calculate their distances with remarkable accuracy. These stars are often found in spiral arms, so they serve as both distance markers and spiral tracers. RR Lyrae stars, on the other hand, are older, lower-mass stars found in globular clusters and the halo. Their consistent brightness makes them excellent tools for measuring distances to ancient stellar populations. Together, these variable stars form a stellar measuring stick that spans both the youthful arms and the ancient outskirts of the Milky Way. Another group that has been crucial to mapping the galaxy are OB associations. These are loose groups of very massive, very hot O and B-type stars. Because they are so bright, they can be seen across great distances, even through some interstellar dust. Their presence marks the most active sites of star formation, and by plotting their locations, astronomers have outlined the Milky Way's major spiral arms with far more precision than before. Stellar populations also reveal the chemical fingerprint of the galaxy. Younger stars in the disk, for example, are rich in heavier elements, what astronomers call metals, because they formed from gas enriched by previous generations of supernova explosions. Older stars, especially those in the halo and globular clusters, have much lower metal content, since they were born in a young universe before many heavy elements existed. By studying this chemical distribution, astronomers can trace the history of star formation across the galaxy and even identify stars that were once part of other galaxies before being captured by the Milky Way's gravity. In recent decades, surveys like Gaia and the Sloan Digital Sky Survey, SDSS, have revolutionized our understanding of these stellar populations. Gaia has provided unprecedented positional and motion data for billions of stars, allowing astronomers to group them by age, motion, and chemical composition. This has revealed streams of stars moving together, remnants of dwarf galaxies shredded by the Milky Way's gravity, as well as precise outlines of spiral arms filled with young, luminous stars. Meanwhile, SDSS and other spectroscopic surveys have measured the light from stars to determine their chemical makeup, creating a kind of family tree of stellar populations that maps not just where stars are, but how the galaxy assembled over billions of years. What emerges from this tapestry of stars is a galaxy that is alive with both youth and age, with stars of every kind weaving the story of its evolution. The massive, short-lived stars shine like cosmic beacons marking spiral arms. The ancient halo stars whisper of a time when the galaxy was just beginning to form. Stars like our Sun tell us about the middle-aged disk where life-sustaining planets can arise. Together, these populations outline the Milky Way's shape, trace its structure, and reveal its staggering scale. And that scale is what comes next. Because by combining all these stellar markers, by measuring their distances, mapping their distributions, and tracing their motions, astronomers have finally been able to give us the most astonishing revelation of all, the actual size of the Milky Way. For centuries, the question of the Milky Way's size loomed as one of astronomy's greatest mysteries. Early star counts by Herschel gave us a tiny, distorted picture. Shapley's work with globular clusters exploded that view, revealing a galaxy far larger than most had dared imagine. But even then, astronomers were cautious. Was the Milky Way tens of thousands of light-years wide, or hundreds of thousands? The dust, the distance problems, and our embedded vantage point meant estimates varied wildly. It is only in recent decades, with the precision of modern tools, that we can finally state with confidence the true scale of our galactic home. The Milky Way is about 100,000 to 120,000 light-years across. To put that into perspective, if you could travel at the speed of light, an impossible feat for us, you would still need more than 100,000 years to go from one edge of the galaxy to the other. Compare that to the entire span of human civilization, which stretches back only about 10,000 years. Our galaxy dwarfs all of human history by orders of magnitude. This size is not uniform. The thin disk, where most of the stars and spiral arms reside, spans this 100,000 to 120,000 light-year diameter. But recent observations suggest that the disk itself extends farther than previously thought, with faint stars and hydrogen gas stretching even beyond that. For a long time, astronomers thought the stellar disk might end sharply, but Gaia's mapping and radio observations of hydrogen have shown that the disk gradually tapers off and may even warp at the edges. Some estimates suggest that faint stars and gas could extend the disk's reach to as much as 150,000 to 200,000 light-years, though the denser, main part of the galaxy remains around 120,000. The thickness of the disk is another striking dimension. While it spans over 100,000 light-years in diameter, the disk is only about 1,000 light-years thick in most places, an incredibly thin ratio compared to its width. Imagine a giant, cosmic pancake, wide and flat, but surprisingly thin relative to its span. There is also a thicker disk component, extending perhaps 3,000 to 4,000 light-years above and below the galactic plane, filled with older stars that have settled into puffier orbits. This thick disk adds another layer of complexity to the Milky Way structure. One of the most exciting results of modern surveys is the discovery that the Milky Way's disk is not perfectly flat but rather warped and twisted at its outer edges. Radio maps of hydrogen gas reveal that the disk bends upward on one side and downward on the other, creating a subtle S-shape. This warp may have been caused by the gravitational tug of smaller satellite galaxies, like the Magellanic Clouds, or by uneven distributions of dark matter in the galactic halo. Whatever the cause, it shows that our galaxy is dynamic, still being shaped by cosmic interactions even today. What's remarkable about this revelation of size is not just the numbers, but what they mean for our place in the cosmos. When Shapley first suggested the Milky Way was over 100,000 light-years wide, It seemed almost unbelievable. Now, with Gaia's billion-star survey, hydrogen maps from radio astronomy, and infrared observations penetrating the dust, we not only confirm this but realize that the galaxy is larger and more intricate than we thought. Humanity has gone from guessing blindly to measuring with confidence, turning mystery into knowledge. And yet, even at 120,000 light-years across, this is only part of the story. The visible disk and spiral arms give us the dazzling structure we recognize, but the galaxy does not end at the disk's edge. Surrounding this bright pinwheel is something far larger and more elusive: the Milky Way's halo, an enormous sphere of dark matter, faint stars, and ancient clusters that stretches hundreds of thousands of light-years beyond the disk. To understand the true scale of our galaxy, we must include this halo, because without it, the Milky Way's mass, rotation, and gravitational influence cannot be explained. Beyond the brilliant spiral arms, the thin and thick disks, and even beyond the central bulge, the Milky Way extends into a realm that is far less obvious to the naked eye: the galactic halo. While the disk presents a luminous, organized structure that is easily visible from Earth under dark skies, the halo is vast, diffuse, and mostly invisible. It stretches hundreds of thousands of light-years beyond the disk, encompassing a volume far larger than the bright stellar disk we usually think of when imagining the Milky Way. Understanding the halo is essential for grasping the true size, mass, and dynamics of our galaxy. The halo is composed of two main components: stars and globular clusters, and dark matter, the mysterious substance that dominates the Milky Way's mass. The stellar halo contains stars that are typically older, less metal-rich, and more sparsely distributed than the stars in the disk. These stars are often relics of the Milky Way's formation and growth, remnants of smaller galaxies that were absorbed billions of years ago. Some of these stars exist in streams, coherent flows left behind as dwarf galaxies were torn apart by the Milky Way's gravity. Observing these stellar streams allows astronomers to trace the galaxy's merger history, essentially reading a fossil record of past galactic collisions. Globular clusters, dense spherical collections of hundreds of thousands of stars, also reside in the halo. They are among the oldest objects in the galaxy, with ages exceeding 12 billion years, nearly as old as the universe itself. Distributed spherically around the galactic center, these clusters serve as markers for the extent of the halo and provide crucial insights into the gravitational potential of the Milky Way. By measuring the velocities and positions of globular clusters, astronomers can infer the mass distribution of the galaxy, including the invisible component, dark matter. Dark matter is the true enigma of the halo. While the stars in the halo are sparse and faint, dark matter dominates the galaxy's mass, forming a vast, invisible sphere that envelopes the Milky Way. This dark matter does not emit, reflect, or absorb light, making it completely undetectable with optical telescopes. Its presence is inferred from its gravitational effects, particularly the way stars in the disk and halo rotate. Without this massive, unseen halo, the outer stars would rotate far more slowly than they actually do, and the galaxy would be torn apart by centrifugal forces. Studies suggest that the dark matter halo extends at least 300,000 to 500,000 light-years from the galactic center, far beyond the visible disk. Its mass is estimated to be several times that of all the stars in the Milky Way combined, making it the dominant gravitational influence in the galaxy. The halo is not uniform or static. Observations show substructures, streams, clumps, and remnants of past galactic mergers, indicating that the Milky Way is still evolving. The Sagittarius stream, for example, is a long ribbon of stars being pulled from the Sagittarius dwarf galaxy as it orbits and gradually merges with the Milky Way. These features reveal that the halo is not merely a smooth, spherical envelope but a dynamic, complex region shaped by billions of years of accretion and interaction with neighboring galaxies. In addition to stars and dark matter, the halo contains hot, ionized gas that extends far beyond the visible disk. This gas plays a role in the galaxy's ongoing evolution, feeding the disk with material that can eventually form new stars. Observations in X-ray and ultraviolet wavelengths have detected this diffuse halo gas, adding another layer to our understanding of the Milky Way's full extent. The combination of stars, clusters, gas, and dark matter means that the Milky Way's gravitational influence extends much farther than the luminous disk. While the disk is about 100,000 to 120,000 light-years across, the full halo stretches several times that distance, encompassing a volume in which even distant dwarf galaxies orbit the Milky Way as satellites. This perspective dramatically enlarges the scale of our galactic home and highlights the difference between what we can see and what actually dominates the galaxy. The halo is not just an abstract concept. It is the structure that holds the Milky Way together, governs its rotation, and links it to the larger cosmic environment. In essence, the halo represents the invisible backbone of the Milky Way. Without it, the luminous disk would be unstable, the stars we see would not rotate. As they do, and the galaxy could not maintain its majestic spiral structure. It also reminds us that what we see is only a fraction of reality. The Milky Way, like the universe itself, contains far more hidden than visible, and it is through careful observation and inference that astronomers can map the unseen components that dominate the cosmos. The halo also provides perspective on the Milky Way's vastness. The disk's diameter of 100,000 to 120,000 light-years is impressive, but when we include the halo, the galaxy's influence stretches out to hundreds of thousands of light-years. This means our home is not just a single luminous structure but a massive, gravitationally bound system whose reach touches, and interacts with, its cosmic neighborhood, including the Magellanic Clouds and other satellite galaxies. Understanding the halo has revolutionized our picture of the Milky Way. Once, astronomers imagined a modest, flat galaxy, with stars organized in a simple disk. Now, we know the galaxy is enveloped in a vast, invisible halo, populated with ancient stars, globular clusters, diffuse gas, and dark matter. It is a structure of staggering complexity, extending far beyond the edges of the disk, providing the gravitational scaffolding for the galaxy, and linking the Milky Way to the universe around it. The Milky Way is not just a structure of spiral arms, disks, and halos. It is a teeming metropolis of stars, each with its own story, age, and potential planetary system. One of the most striking features of our galaxy is its sheer stellar population. Current estimates place the number of stars in the Milky Way at roughly 200 to 400 billion. This enormous range reflects the challenges of counting stars that are hidden by dust, faint dwarfs too dim to detect, or distant halo stars that blend into the background. Regardless of the exact number, it is clear that the Milky Way is a vast city of stars, and each one contributes to the galaxy's luminosity, gravitational pull, and cosmic history. Among these stars, there is an incredible diversity. There are massive, short-lived blue stars that burn through their fuel in mere millions of years and end in spectacular supernova explosions, seeding the galaxy with heavy elements. There are stars like our Sun, medium-sized and stable, capable of supporting planets and, potentially, life. Then there are red dwarfs, small, faint, and long-lived, making up the majority of stars in the galaxy. These stars are dim and difficult to detect at great distances, which is why earlier estimates of the Milky Way's size and stellar content were so uncertain. By combining surveys of bright stars, faint stars, and the underlying mass inferred from motions, astronomers have refined their understanding of the galaxy's population. But the Milky Way is not just a collection of stars. Each star may host planets, and current research suggests that planets are exceedingly common. Estimates indicate that our galaxy could contain hundreds of billions of planets, ranging from massive gas giants like Jupiter to rocky worlds like Earth, and even smaller, dimmer objects. Some stars may host multiple planets, forming entire planetary systems that, in aggregate, may outnumber the stars themselves. This revelation reshapes our understanding of the Milky Way, not just as a stellar city, but as a galaxy filled with countless potential worlds, some of which could harbor life. The galaxy also contains nebulae, vast clouds of gas and dust where stars are born or where stars have died. Star-forming regions like the Orion Nebula glow brightly as young stars illuminate the surrounding gas. Planetary nebulae mark the final stages of medium-sized stars, shedding their outer layers into space and enriching the interstellar medium. Supernova remnants scatter heavier elements across the galaxy, creating the raw materials for future generations of stars and planets. These nebulae, while far fewer in number than individual stars, play an outsized role in the Milky Way's evolution, driving cycles of birth, death, and rebirth. Then there are the black holes, invisible yet profoundly influential. Every massive star that ends its life in a supernova may leave behind a black hole, and some of these lie in the disk, halo, or near the galactic center. The most famous is Sagittarius A, a supermassive black hole at the center of the galaxy with a mass of about 4 million suns. But many stellar mass black holes are scattered throughout, quietly shaping the dynamics of their local neighborhoods through gravity. While we cannot see them directly, we detect their presence via X-ray emissions from accreting material or by observing their gravitational effects on nearby stars. Estimates suggest the Milky Way may contain tens of millions of stellar mass black holes, a hidden population contributing to the galaxy's mass and structure. In addition to stars, planets, nebulae, and black holes, the Milky Way contains smaller objects such as brown dwarfs, often called failed stars because they never ignited hydrogen fusion in their cores. Though dim and difficult to detect, these objects are likely numerous and contribute to the overall mass of the galaxy. There are also rogue planets, drifting unbound through the galaxy, remnants of chaotic formation processes or ejected from their parent systems. Each of these populations adds layers of complexity to the Milky Way, making it not just a stellar disk but a dynamic ecosystem of matter in all forms. This astonishing variety of objects is not merely decorative, it has practical implications for understanding the galaxy. Counting stars and determining their distribution allows astronomers to estimate the total mass of the Milky Way, model its gravitational influence, and measure its rotation. Mapping nebulae and star-forming regions reveals where the galaxy is actively producing new stars, while tracking black holes and globular clusters uncovers clues about past galactic mergers and the evolution of the halo. In short, the galaxy's population is both its identity and its record book, encoding the history of 13.6 billion years of cosmic evolution. To summarize, the Milky Way is home to approximately 200 to 400 billion stars, each potentially hosting planets, and surrounded by countless nebulae, black holes, and other celestial objects. This immense population traces the spiral arms, fills the disk and halo, and underlies the galaxy's gravitational structure. The scale of this population is staggering, more stars than we can possibly imagine, each with the potential for complex systems and possibly even life. With this understanding of the galaxy's stellar population, we can begin to put its size into perspective by comparing it to neighboring galaxies. Some of these galaxies are larger, some smaller, but all provide context for just how immense and intricate our Milky Way truly is. When we consider the Milky Way, it is natural to ask, how does our galaxy compare to the vast array of galaxies in our cosmic neighborhood? The Milky Way, impressive though it is just one of billions of galaxies in the universe. But within the local group, the collection of galaxies bound together by gravity, our galaxy has both peers and giants, providing crucial context for its size, mass, and structure. Comparing the Milky Way to its neighbors helps us appreciate its grandeur and its place in the cosmic hierarchy. The most famous of our neighboring galaxies is Andromeda, M31, located approximately 2.5 million light-years from the Milky Way. Andromeda is a massive spiral galaxy, similar in structure to the Milky Way, with a well-defined disk, spiral arms, and a central bulge. Estimates suggest that Andromeda may contain over a trillion stars, roughly 2 to 3 times the number of stars in our galaxy. In terms of size, Andromeda's disk spans about 220,000 to 250,000 light-years, roughly twice as wide as the Milky Way's 100,000 to 120,000 light-year disk. Its massive halo and satellite galaxies extend even further. Despite being larger, Andromeda shares many structural similarities with the Milky Way, including a central bar and spiral arms traced by young stars and star-forming regions. Then there is the Large Magellanic Cloud, LMC, one of the Milky Way's satellite galaxies. The LMC is far smaller, with a diameter of roughly 14,000 to 15,000 light-years, barely a fraction of the Milky Way's size. It contains tens of billions of stars, many of which are young, and is actively forming new stars in regions like the 30 Doradus Nebula, also known as the Tarantula Nebula. Its proximity, only about 160,000 light-years from the Milky Way, allows astronomers to study star formation, galactic interaction, and tidal forces in real time. While the LMC is much smaller than the Milky Way, its gravitational influence and tidal interactions have helped shape the warp of our galaxy's disk, demonstrating that even minor neighbors can leave a mark on a giant like the Milky Way. The Small Magellanic Cloud, SMC, is another satellite galaxy, smaller still, with a diameter of about 7,000 light-years. Though tiny compared to the Milky Way, the SMC's interactions with both the LMC and the Milky Way create streams of stars and gas, such as the Magellanic Stream, which stretches across hundreds of thousands of light-years. These interactions illustrate how galaxies, regardless of size, are dynamic systems, constantly influencing each other over cosmic time. Another interesting comparison comes from Triangulum M33, a medium-sized spiral galaxy in the local group. Triangulum's disk is roughly 60,000 light-years across, making it about half the size of the Milky Way. It contains tens of billions of stars and prominent spiral arms, though it lacks the massive bar seen in our galaxy. Studying M33 provides astronomers with insights into how spiral galaxies of different sizes form and evolve, offering a mirror to examine the Milky Way in a broader context. By comparing these galaxies, we can see that the Milky Way occupies a middle position in terms of size and mass. It is smaller than Andromeda, the local group's giant, yet much larger than its satellite galaxies, like the LMC and SMC. Its stellar population is immense, its spiral arms extensive, and its halo massive, making it a dominant player in our corner of the universe. These comparisons also reinforce the scale of the Milky Way. Even our galaxy, with over 200 billion stars and a disk spanning over 100,000 light-years, is dwarfed by larger spirals or hidden in the crowd of more massive galaxies beyond the local group. The Milky Way's interactions with these neighbors are also essential to its evolution. Tidal forces from the LMC, SMC, and other smaller galaxies may have contributed to the warp in the Milky Way's disk, the streams of stars in the halo, and even the inflow of gas that fuels ongoing star formation. In billions of years, the comparison with Andromeda becomes even more dramatic. Gravitational attraction is slowly drawing the two giants together, setting the stage for a collision that will merge them into a single massive galaxy. These comparisons help us place humanity's home galaxy in perspective. The Milky Way is enormous on a human scale and spectacular in its stellar population, spiral arms, and dark matter halo. Yet it is just one galaxy among many, bound in a cosmic community of interacting neighbors, each influencing the others through gravity and time. The Milky Way may feel eternal and unchanging when we look up at the night sky, but in the grand scope of the local group, it is part of a dynamic system, growing, interacting, and slowly moving toward future transformations. By understanding its size relative to Andromeda, the Magellanic Clouds, and Triangulum, we gain a deeper appreciation for the Milky Way's scale, structure, and complexity. This comparison also sets the stage for understanding our exact location within the galaxy, which is essential for mapping, measuring, and exploring its structure from the inside out. Amid the vastness of the Milky Way, filled with hundreds of billions of stars and sprawling spiral arms, our solar system occupies a modest but precisely measurable location. We are not perched at the center of the galaxy, nor at its distant outskirts, but rather in a relatively quiet neighborhood, a middle suburb of the Milky Way's enormous disk. This location profoundly shapes our perspective of the galaxy, influencing what we can see, how we interpret the night sky, and even how astronomers have been able to map the galaxy from within. Our solar system resides approximately 27,000 light-years from the galactic center. To put this in perspective, if the Milky Way's disk spans roughly 120,000 light-years, we are situated about a quarter of the way in from the edge to the center, comfortably within the disk but far from its heart. This positioning has advantages and disadvantages. On the one hand, we are far enough from the dense, chaotic regions of the central bulge to enjoy a relatively stable gravitational environment, where stars are spaced widely enough to reduce the risk of catastrophic stellar encounters. On the other hand, being embedded within the disk means that much of the Milky Way structure, particularly the far side of the galaxy and certain spiral arms, is obscured by dust, complicating our efforts to measure its full extent. We are located specifically in a minor spiral feature known as the Orion Arm, also called the Orion Spur. This is a smaller arm or spur that lies between the two major arms known as the Sagittarius and Perseus arms. Unlike these dominant arms, which host vast star-forming regions and dense concentrations of young stars, the Orion Arm is relatively modest, containing a mixture of young and old stars, gas clouds, and stellar clusters. It is within this arm that the Sun and its planets, including Earth, reside, a cosmic neighborhood that has been conducive to the development of life and the stability of planetary orbits over billions of years. The Orion Arm itself is an important marker in mapping the galaxy. Astronomers use the stars, gas, and star-forming regions within this arm as reference points to triangulate distances to other spiral arms. Because we sit inside the Orion Arm, our perspective is inherently edge-on, meaning we primarily see the galaxy as a band of light stretching across the night sky. This vantage point is excellent for local measurements and parallax studies, but makes it challenging to visualize the Milky Way as a whole, which is why early astronomers struggled to determine its shape and size. Beyond our immediate arm, the Milky Way structure becomes increasingly complex. The Orion spur itself is thought to be a bridge of stars connecting the Sagittarius and Perseus arms, possibly formed by gravitational interactions within the disk or by density waves that create the spiral pattern. Embedded within this spur are several stellar nurseries, such as the Orion Nebula, the Taurus Molecular Cloud, and the Pleiades Cluster, providing astronomers with rich laboratories to study star formation. These local features are among the brightest and most prominent in our night sky, yet they are just tiny fragments of the larger galactic tapestry. Being 27,000 light-years from the center also places us in an advantageous position for observing the galactic center itself. From our vantage point, we can peer towards Sagittarius, where the central bulge and the supermassive black hole, Sagittarius A, reside, while also looking outward toward the galaxy's spiral arms and the halo beyond. This intermediate location allows astronomers to study the Milky Way in 3 dimensions: inward toward the core, along the disk, and outward into the halo. In terms of galactic rotation, our location has interesting implications. The solar system, along with nearby stars, orbits the galactic center at roughly 220 kilometers per second, completing one orbit every 225 to 250 million years, a period sometimes referred to as a galactic year. This motion carries us through different regions of the Orion Arm and, over time, past various molecular clouds and stellar clusters. While the motion is imperceptible on human timescales, over millions of years it plays a role in influencing the gravitational environment of the solar system and potentially the influx of cosmic material into our neighborhood. Finally, our location gives context to the Milky Way scale and structure. Being within the disk, roughly halfway out from the center, allows us to trace spiral arms, study stellar populations, and measure galactic rotation. Yet it also reminds us that we cannot see the galaxy from the outside. We are limited to indirect methods, using stellar distances, gas distributions, and modern surveys to reconstruct the full spiral pattern. Without knowing our position in the Orion Arm, attempts to map the Milky Way would be far less precise. In summary, the solar system resides in the Orion Arm, about 27,000 light-years from the galactic center, nestled in a relatively calm and stable part of the disk. This placement has shielded us from the densest, most chaotic regions while offering a rich vantage point to study the structure, dynamics, and evolution of our galaxy. Our position, neither central nor peripheral, provides a perfect laboratory to understand both the Milky Way itself and its interactions with the cosmic neighborhood. At the very heart of the Milky Way lies a region of extreme gravity, immense density, and staggering energy, the galactic center. While the spiral arms, disk, and halo contain billions of stars and a complex distribution of gas and dust, it is the central region that governs the galaxy's overall dynamics. This is where the galaxy's mass is concentrated and where the most exotic objects reside, including Sagittarius A, a supermassive black hole that anchors the Milky Way and shapes its gravitational landscape. Sagittarius A, often abbreviated as SGR-A, is not a typical black hole, it is gargantuan. Its mass is estimated at roughly 4 million times that of the Sun, concentrated in a region smaller than the orbit of Mercury. This makes it an incredibly dense point in space, where gravity is so strong that nothing, not even light, can escape its event horizon. Despite this, SGR-A does not dominate the galaxy in luminosity. Unlike the active black holes in some distant galaxies, which emit enormous amounts of radiation as they devour surrounding material, our supermassive black hole is relatively quiet, accreting matter at a slow rate. Its quiet nature makes it more challenging to study, but astronomers have used ingenious methods, such as tracking the orbits of nearby stars, to reveal its presence and measure its mass with astonishing precision. The galactic center itself is a highly dense and energetic region, packed with stars, gas clouds, and dust. Within just a few light-years of Sagittarius A, stars orbit at incredible velocities, some reaching thousands of kilometers per second. By observing these rapid orbits using infrared telescopes, astronomers can apply Newtonian and relativistic mechanics to calculate the mass of SGR-A. The results leave little doubt. A supermassive black hole resides at the core of our galaxy. Beyond the black hole, the galactic center contains a dense stellar bulge composed mainly of older, metal-rich stars. This bulge extends several thousand light-years in all directions and forms a roughly spherical, though slightly elongated, distribution around the center. Stars in this bulge move in complex orbits, unlike the orderly circular motion seen in the disk. Some stars even plunge close to Sagittarius A, following highly elliptical paths that reveal the extreme gravitational influence of the central black hole. The region is also rich in gas and dust, forming complex clouds and filaments that feed star formation. Some of these clouds are heated by intense radiation from massive young stars, creating glowing nebulae that can be observed in infrared and radio wavelengths. Supernova remnants and energetic phenomena near the center also contribute to a turbulent environment, making the galactic center one of the most extreme and dynamic regions in the Milky Way. One of the most fascinating aspects of SGR-A is how it shapes the galaxy's gravitational structure. The black hole's immense mass is not responsible for the entire gravitational pull of the Milky Way. That role is dominated by the stars, gas, and dark matter halo. But it does anchor the central bulge and contribute to the orbits of stars in the inner few thousand light-years. Its presence influences how stars move, how gas is channeled toward the center, and how the bar and inner spiral structure maintain their integrity over billions of years. Modern observations of SGR-A have been revolutionary. Using infrared telescopes like the Very Large Telescope, VLT, in Chilean radio interferometers like the Event Horizon Telescope, EHT, astronomers can probe the environment just outside the black hole's event horizon. These instruments have imaged the shadow of SGR-A, revealing the bending of light caused by extreme gravity and providing direct evidence for Einstein's theory of general relativity in one of its most extreme environments. These observations not only confirm the black hole's existence but also allow us to study the behavior of matter under conditions impossible to replicate on Earth. The galactic center is not just a static structure. It is dynamic and evolving. Gas clouds occasionally spiral inward, feeding SGR-A and creating bursts of radiation detectable in X-ray and infrared wavelengths. Stars are born and die rapidly in this environment, and gravitational interactions continually stir the central region. Over millions of years, these processes shape the central bulge, influence the inner spiral arms, and contribute to the ongoing evolution of the Milky Way as a whole. Understanding the galactic center also provides context for the solar system's location. At 27,000 light-years away, we are far enough from the violent central region to enjoy relative stability, avoiding the hazards of high stellar density, supernovae, and intense radiation. Yet our distance is close enough to allow detailed observation of SGR-A and the surrounding bulge, giving humanity a privileged vantage point from which to study the extreme physics of supermassive black holes. In short, the galactic center is the beating heart of the Milky Way, anchored by Sagittarius A, a supermassive black hole whose gravity governs the inner galaxy, influences spiral structure, and provides a laboratory for studying extreme physics. The dense stellar bulge, turbulent gas clouds, and exotic phenomena surrounding it are a testament to the power and complexity of our galaxy, reminding us that even amid hundreds of billions of stars, the center exerts a profound influence on the entire system. One of the most fundamental features of the Milky Way is its rotation. Far from being a static structure, the galaxy is in constant motion. Every star, gas cloud, and dust particle is orbiting the galactic center under the influence of gravity. This rotation is a key to understanding not only the Milky Way structure but also its mass distribution, the presence of dark matter, and the long-term dynamics that shape spiral arms, bars, and star formation patterns. The stars in the disk, including our own Sun, follow approximately circular orbits around the galactic center. The rotation is differential, meaning that stars closer to the center orbit faster than those further out, but not in the same way as planets orbiting the Sun. Unlike a simple Keplerian system where outer objects slow dramatically, the Milky Way's rotation curve is surprisingly flat. Observations show that stars at the Sun's radius, about 27,000 light-years from the center, orbit at roughly 220 to 240 kilometers per second, and stars much farther out in the disk orbit at nearly the same speed. This uniformity was one of the first hints for the presence of dark matter, which provides the extra gravitational pull necessary to maintain this nearly constant rotational speed far from the galaxy's visible mass. To grasp the scale, consider the orbital period of the Sun. At 27,000 light-years from the center, our solar system takes about 225 to 250 million years to complete one orbit around the Milky Way. This is sometimes called a galactic year. Since the formation of the solar system roughly 4.6 billion years ago, the Sun has completed about 20 full orbits around the center of the galaxy. During each orbit, it has passed through spiral arms, near giant molecular clouds, and across varying regions of interstellar gas and dust, all while maintaining a relatively stable trajectory. Stars closer to the galactic center move much faster. In the dense inner bulge, stars may orbit at several hundred kilometers per second, completing circuits in just tens of millions of years. These rapid motions, combined with the gravitational pull of Sagittarius A, create a highly dynamic environment where interactions between stars are more frequent and orbital paths are more elliptical and chaotic. In contrast, stars in the outer disk move more slowly and follow more circular orbits, tracing the grand spiral structure from afar. Gas in the disk, particularly hydrogen clouds observed via 21-centimeter radio emission, follows the rotation pattern of the stars but also exhibits subtle deviations due to spiral density waves. These density waves are regions of higher gravitational potential that compress gas and trigger star formation. As the disk rotates, stars and gas enter and exit these waves, creating the spiral arm structure we observe today. This interplay between rotation, gravity, and density waves is fundamental to the galaxy's ongoing evolution. The rotation curve of the Milky Way, how orbital speed changes with distance from the center, is a vital diagnostic tool. When astronomers first measured it in the mid-20th century, they expected the outer stars to slow down dramatically, following a Keplerian decline similar to the planets in the solar system. Instead, they found a flat rotation curve, meaning the outer stars orbit just as quickly as those closer in. This unexpected result was among the first strong evidence for the existence of dark matter, an invisible halo surrounding the galaxy that provides additional gravitational pull. The halo's influence ensures that the outer stars do not drift away, keeping the galaxy bound together over billions of years. Rotation also affects the shape of the galaxy. The centrifugal force from rotation helps flatten the disk, while the slower rotation of the halo stars contributes to a more spheroidal distribution in the bulge and halo. It also influences the dynamics of the spiral arms, bars, and star-forming regions. Over time, differential rotation can stretch out structures, redistribute gas, and create patterns in the orbits of stars, which can be traced by precise measurements of their motions using surveys like Gaia. Interestingly, rotation is not uniform in all directions. Stars in the thick disk and halo often have more elliptical or inclined orbits, moving in and out of the plane of the disk. These populations preserve the memory of past mergers, interactions, and accretion events. By comparing the rotation of stars in different components, thin disk, thick disk, bulge, and halo, astronomers can reconstruct the formation history of the Milky Way, determining which parts formed early, which were shaped by mergers, and how the galaxy grew over billions of years. Even the Sun's orbit through the galaxy has subtle consequences. As it travels, it occasionally passes through spiral arms, encountering regions of higher gas density. These passages may influence the rate of cometary impacts in the solar system, trigger waves of star formation in nearby molecular clouds, or modulate the cosmic radiation environment. Although these effects are subtle and occur over millions of years, they demonstrate how rotation links local and galactic scale processes. In short, the Milky Way's rotation is a defining feature. Stars take hundreds of millions of years to complete their orbits, moving in a delicate balance between gravitational pull and centrifugal motion. Differential rotation sculpts the spiral arms, maintains the disk shape, and interacts with the halo to produce the flat rotation curve that points to dark matter. Without this rotation, the galaxy could not maintain its structure, and the intricate dance of stars, gas, and dust that defines the Milky Way would unravel. One of the most profound revelations about the Milky Way, and galaxies in general, is that what we can see accounts for only a small fraction of what is actually there. The bright stars, glowing nebulae, and observable gas are just the tip of the iceberg. To explain the Milky Way's size, rotation, and gravitational behavior, astronomers must invoke a mysterious, invisible substance known as dark matter. This enigmatic material does not emit, absorb, or reflect light, making it undetectable through traditional telescopes. Yet its presence dominates the galaxy, shaping everything from the motion of stars to the stability of the spiral arms. The first clues pointing to dark matter arose from the study of galactic rotation curves. When astronomers measured how fast stars orbited the Milky Way at different distances from the center, they found something unexpected. Based on the visible mass, stars, gas, and dust, stars in the outer regions should rotate more slowly, much like the planets in our solar system, where Mercury races around the Sun in 88 days while Neptune takes 165 years. Instead, stars far from the galactic center move as fast as those closer in, maintaining nearly constant orbital speeds even hundreds of thousands of light-years from the core. This discrepancy cannot be explained by visible matter alone. To account for this flat rotation curve, scientists concluded that the Milky Way is embedded within a massive halo of dark matter, extending well beyond the visible disk. Estimates suggest that dark matter constitutes roughly 85 to 90% of the galaxy's total mass, dwarfing the combined mass of all stars, gas, and dust. Without this invisible component, the outer stars would not have sufficient gravitational pull to remain bound to the galaxy. They would simply drift off into intergalactic space. Dark matter, therefore, is the unseen scaffold holding the Milky Way together, providing the gravitational glue necessary to maintain its structure and dynamics. Dark matter also explains the Milky Way's enormous size. While the stellar disk spans about 100,000 to 120,000 light-years, the influence of dark matter extends far beyond, into the halo that stretches hundreds of thousands of light-years. This halo is not uniform. It likely has a spherical or slightly oblate shape, with density decreasing gradually with distance from the center. The halo encompasses satellite galaxies, globular clusters, and streams of stars, binding them gravitationally to the Milky Way and preventing them from escaping. Without this invisible halo, the galaxy would be far smaller and less massive than it appears. Observations of galaxy interactions provide additional evidence for dark matter. The Milky Way is gravitationally interacting with nearby galaxies, such as the large and small Magellanic Clouds, as well as the distant Andromeda Galaxy. The gravitational pull exerted on these galaxies, and the way they move through space, can only be explained if the Milky Way has a much larger mass than is accounted for by visible matter alone. Dark matter provides this extra mass, ensuring that these interactions and orbital dynamics match observations. Dark matter also influences the formation and stability of the Milky Way's spiral arms. Spiral structures are thought to arise from density waves, regions of enhanced gravitational potential that move through the disk. The overall mass distribution, including dark matter, determines the strength and pattern of these waves. Without the additional gravitational pull of dark matter, the spiral arms would be weaker, less coherent, or might even dissipate over time. In this sense, dark matter is not just a passive presence. It actively shapes the galaxy's visible structure. The presence of dark matter is also revealed by stellar streams and the orbits of globular clusters in the halo. Many streams, remnants of dwarf galaxies torn apart by the Milky Way's gravity, move along paths that indicate a stronger gravitational field than the visible matter can provide. Similarly, the dynamics of globular clusters at extreme distances from the galactic center suggest the presence of a massive, invisible halo. These observations reinforce the idea that the Milky Way's gravitational influence extends far beyond the luminous disk, entirely due to dark matter. Despite decades of study, dark matter remains one of the greatest mysteries in astrophysics. Its exact nature is unknown. It could be exotic particles, weakly interacting massive particles, WIMPs, or some entirely new form of matter. Detecting it directly has proven extremely difficult, yet its gravitational fingerprints are unmistakable. Without dark matter, the Milky Way would look dramatically different. Its rotation curve would drop off sharply, its halo would be far smaller, and many of the satellite galaxies and streams would not be gravitationally bound. In summary, dark matter is essential to understanding the Milky Way's size, rotation, and mass distribution. While the luminous stars and gas provide a stunning visual picture, they tell only a fraction of the story. The invisible halo of dark matter dominates the galaxy, holding the outer stars in orbit, shaping spiral arms, and binding satellites and streams across vast distances. It is a silent but powerful presence, demonstrating that the majority of our galaxy, and indeed the universe, is composed of something fundamentally different from the matter we can see. The story of mapping the Milky Way took a revolutionary turn with the advent of radio astronomy. For centuries, astronomers relied on optical telescopes to observe stars, nebulae, and other luminous features in visible light. While these instruments revealed much, they were severely limited by interstellar dust, which obscures large portions of the galaxy, especially along the dense plane of the disk. The solution came in the form of radio waves, longer wavelengths of light that can penetrate dust clouds, allowing scientists to chart the Milky Way in ways never before possible. At the heart of this radio revolution is neutral hydrogen, Hi, the most abundant element in the galaxy. Neutral hydrogen emits radiation at a wavelength of 21 centimeters, known as the hydrogen line. This emission is faint but detectable across vast distances. Since hydrogen gas is distributed throughout the galactic disk, and particularly concentrated in the spiral arms, mapping 21 centimeters emissions provides a detailed three-dimensional view of the galaxy's structure. Unlike stars, which may be obscured by dust or limited by brightness, hydrogen gas fills the gaps, revealing the skeletal framework of the Milky Way. The first large-scale 21 centimeters surveys began in the mid-20th century and were groundbreaking. By measuring the Doppler shifts of the hydrogen emission, astronomers could determine the velocity of gas along the line of sight. Using models of galactic rotation, these velocities were converted into distances, allowing researchers to construct maps of the spiral arms, including regions invisible in optical light. The results were astonishing. The Milky Way's spiral structure was far more extensive and intricate than previously imagined. One of the key advantages of radio surveys is their ability to detect spiral arms on the far side of the galaxy, which optical telescopes cannot see due to intervening dust. For example, the Perseus arm and the outer arm, two major spiral features, were largely inaccessible to visible light observations but became apparent in radio surveys. These maps revealed not only the positions of the arms but also their pitch angles, lengths, and how they wrap around the galactic center. The hydrogen gas essentially illuminates the Milky Way scaffolding, allowing astronomers to trace its spiral architecture across the disk. Radio observations also uncovered warps and distortions in the outer disk. By mapping Hi at different galactic latitudes and longitudes, astronomers detected bends in the disk, suggesting gravitational interactions with satellite galaxies like the Large and Small Magellanic Clouds. These warps are subtle, often only a few thousand light-years in amplitude, but they provide clues about the Milky Way's dynamical history, including past mergers, tidal interactions, and the influence of the dark matter halo. Beyond neutral hydrogen, radio surveys have been complemented by molecular line observations, such as carbon monoxide, CO, which trace denser regions where stars are actively forming. By combining Hi and CO data, astronomers can identify the full spiral structure, from the diffuse hydrogen gas outlining the arms to the dense molecular clouds where new stars ignite. This dual approach has allowed us to map the Milky Way with unprecedented precision, connecting the gaseous skeleton to the stellar population. One of the most ambitious modern surveys is the Hi4Pi survey, which covers the entire sky with high-resolution 21 centimeters measurements. Combined with data from Gaia and other stellar surveys, astronomers can now align the hydrogen-based spiral map with the positions of young stars, star clusters, and H2 regions. This synergy provides a remarkably detailed and three-dimensional picture of the Milky Way, revealing the size, shape, and orientation of spiral arms across the disk. The impact of these radio surveys goes beyond mapping. By studying the velocity distribution of hydrogen gas, astronomers can infer the galaxy's mass distribution, including the contribution of dark matter. Gas motions in the outer disk help confirm that the rotation curve remains flat far beyond the visible stars, reinforcing the need for a massive, unseen halo. Furthermore, hydrogen observations have traced streams of gas falling into the Milky Way from intergalactic space or from disrupted dwarf galaxies, showing that the galaxy continues to grow and evolve. Radio mapping also revealed that the Milky Way is larger than previously thought. Earlier optical surveys underestimated the disk's extent due to dust obscuration. The 21 centimeters emission traced spiral arms stretching well beyond 120,000 light-years, and faint gas in the outer disk suggests the galaxy's disk may extend even further. These discoveries have refined our understanding of the Milky Way's size, structure, and mass, bridging the gap between stellar maps and the invisible dark matter halo. In essence, radio surveys of hydrogen gas have provided a cosmic X-ray vision of our galaxy, allowing astronomers to see through dust, trace spiral arms across enormous distances, detect warps and distortions, and connect the gaseous structure to the stellar population. Without these observations, our view of the Milky Way would remain incomplete, limited to the stars we can see with optical telescopes and leaving vast portions of the galaxy hidden from our understanding. As astronomers have mapped the Milky Way in ever greater detail, both through optical and radio observations, a picture of the galaxy has emerged that is far more dynamic and complex than the simple spiral we once imagined. The more we look, the more surprises the Milky Way reveals, features that defy our early assumptions and demonstrate that our galaxy is an active, evolving system rather than a static disk of stars. Among the most fascinating of these discoveries are the warped edges of the disk and the streams of stars pulled in from dwarf galaxies, both providing insights into the Milky Way's past interactions and ongoing evolution. One of the earliest and most striking surprises is the warp in the outer disk. While the central regions of the Milky Way are relatively flat, observations of neutral hydrogen gas at 21 cm wavelengths and distant stars reveal that the disk bends upward on one side and downward on the other, forming an S-shaped warp. This phenomenon is subtle but unmistakable. The stellar and gaseous plane of the galaxy is no longer a perfectly flat sheet but a gently twisting ribbon extending across hundreds of thousands of light-years. The warp is not uniform. The amplitude and angle vary depending on the galactic radius and the location in the disk. The origin of this warp has been the subject of extensive study. One leading explanation involves the gravitational influence of satellite galaxies, particularly the Large and Small Magellanic Clouds. As these dwarf galaxies orbit the Milky Way, their gravity pulls on the outer disk, creating a bending effect. Dark matter may amplify this influence, as the halo acts as a medium through which gravitational forces are transmitted, subtly reshaping the disk over time. The warp illustrates that the Milky Way is not isolated. It is part of a cosmic web of interactions that continues to mold its structure even today. Another surprising feature revealed by modern surveys is the presence of stellar streams, long, coherent trails of stars extending across vast portions of the halo. These streams are remnants of dwarf galaxies or globular clusters that have been gravitationally shredded by the Milky Way. One of the best-known examples is the Sagittarius stream, produced by the Sagittarius dwarf spheroidal galaxy as it orbits and gradually merges with the Milky Way. The stars in the stream follow elongated paths, tracing the orbit of their former host and providing a fossil record of the galaxy's accretion history. The discovery of these streams has profound implications. First, they show that the Milky Way is still growing, assimilating smaller galaxies into its halo and disk. These mergers contribute stars, gas, and dark matter, subtly altering the galaxy's mass distribution and rotation. Second, stellar streams act as gravitational probes, allowing astronomers to map the shape and distribution of dark matter in the halo. By measuring the velocities and positions of stars in these streams, scientists can infer the invisible mass that dictates their paths, providing one of the few ways to study dark matter directly. In addition to streams from dwarf galaxies, surveys like Gaia have revealed thousands of smaller stellar substructures in the halo. Some are remnants of ancient mergers, over 10 billion years old, while others are more recent, indicating that the Milky Way's assembly is ongoing. These structures are often subtle and diffuse, detectable only through precise measurements of stellar positions, motions, and chemical compositions. They provide a detailed record of the galaxy's growth and highlight the dynamic nature of even seemingly empty regions of the halo. Warps and streams are not the only surprises. Observations have uncovered ripples, corrugations, and flares in the disk, suggesting that interactions with satellite galaxies or passing dark matter subhalos can induce waves through the stellar disk. These oscillations are subtle vertical displacements of stars above and below the plane, extending thousands of light-years, and they reflect the ongoing dynamical evolution of the galaxy. Such discoveries challenge the traditional view of a smooth, static spiral galaxy, revealing instead a complex, living structure constantly responding to external and internal forces. Together, these surprises, warped edges, stellar streams, and disk ripples, underscore a critical lesson. The Milky Way is not a fixed system frozen in time. It is cosmically active, growing through accretion, interacting with neighbors, and responding to the gravitational pull of dark matter. Even in regions where stars appear sparse, hidden processes shape the structure, distribution, and motion of the galaxy over millions and billions of years. These discoveries also inform our understanding of stellar populations and halo structure. Streams contain stars of varying ages and chemical compositions, often differing from those native to the Milky Way. By studying them, astronomers can identify stars that were once part of other galaxies, distinguishing between native and accreted populations. The warp and ripples in the disk similarly provide insights into how the Milky Way responds dynamically to external perturbations, including the gravitational influence of satellite galaxies, the dark matter halo, and even interactions with intergalactic gas streams. In essence, these surprises transform the Milky Way from a simple spiral pattern into a dynamic, interactive galaxy. Its structure is the product of billions of years of formation, accretion, and gravitational interplay. The warped disk shows how the galaxy responds to tidal forces. Stellar streams reveal its cannibalistic growth. Ripples and flares expose the subtle ongoing interactions that continue to shape its evolution. Even though we reside in a relatively calm neighborhood like the Orion Arm, the broader galaxy is alive with motion, memory, and history encoded in its stars and gas. The Milky Way is not an isolated island in the cosmos. It exists within a rich and dynamic environment known as the Local Group, a gravitationally bound collection of more than 50 galaxies. Understanding the Milky Way's neighborhood provides crucial context for its evolution, interactions, and future trajectory. The Local Group is dominated by three major galaxies: the Milky Way, Andromeda, M31, and Triangulum, M33, with the remaining members being smaller satellite galaxies, dwarf spheroidals, and irregular systems scattered throughout the group. The Milky Way and Andromeda are the giants of the Local Group, each containing hundreds of billions of stars and vast dark matter halos that extend far beyond their luminous disks. Together, these two galaxies account for the bulk of the group's mass. Triangulum is smaller, yet still a significant spiral galaxy, and many of the Local Group's smaller members orbit these giants, forming intricate systems of satellites and streams. The Milky Way itself has more than 50 known satellite galaxies, including the large and small Magellanic Clouds, Sagittarius Dwarf, and Fornax. These satellites are gravitationally bound to the Milky Way and play an active role in its evolution. The interactions within the Local Group are dynamic and ongoing. Satellite galaxies experience tidal forces as they orbit the Milky Way, which can strip stars and gas, forming stellar streams and gaseous trails. A prominent example is the Magellanic Stream, a massive ribbon of gas pulled from the large and small Magellanic Clouds due to their close gravitational interactions with our galaxy. Similarly, the Sagittarius Stream originates from the Sagittarius Dwarf Galaxy, which is being gradually torn apart as it orbits the Milky Way, contributing stars to the halo and subtly altering the galaxy's mass distribution. The Milky Way also interacts gravitationally with its most massive neighbor, Andromeda. The two galaxies are moving toward each other at roughly 110 kilometers per second, and in about 4 billion years, they are predicted to collide and merge. This future event, far beyond human timescales, will drastically reshape the structure of both galaxies, likely forming a massive elliptical or lenticular galaxy. Even now, the gravitational influence of Andromeda is detectable in the motions of stars and satellite galaxies at the outskirts of the Milky Way. The Local Group is therefore a dynamic environment, with galaxies constantly tugging on one another, exchanging matter, and shaping each other's evolution. Smaller galaxies in the Local Group are also affected by these gravitational interactions. Many dwarf spheroidals show distorted shapes, tidal tails, and stripped gas, evidence of past encounters with the Milky Way or Andromeda. These interactions not only provide material for the Milky Way's halo, but also allow astronomers to study the processes of galaxy formation and accretion in real time. The Local Group is, in effect, a laboratory for understanding how galaxies grow by absorbing smaller systems, a process that has been ongoing for billions of years. The dark matter halos of the Milky Way and Andromeda extend far beyond their luminous disks, overlapping in some regions. This dark matter dominance ensures that interactions are not limited to visible stars and gas. The unseen gravitational pull governs the orbits of satellites, the formation of streams, and the eventual collision between massive galaxies. Without dark matter, the dynamics of the Local Group would be radically different, and many smaller galaxies might escape rather than remain bound. Studying the Local Group also provides insights into the Milky Way's past accretion history. Stellar streams, remnants of disrupted dwarf galaxies, and halo substructures all indicate that the Milky Way has grown by absorbing smaller neighbors over cosmic time. By comparing these features with the population of satellite galaxies and the motions of Andromeda and Triangulum, astronomers can reconstruct the assembly history of the Milky Way and predict its future evolution within the group. Additionally, the Local Group is not static. It is part of a larger supercluster environment. The Milky Way, along with the local group, moves toward the Virgo cluster at a velocity of several hundred kilometers per second, pulled by the collective gravity of nearby galaxy clusters. This cosmic motion highlights that even our relatively local neighborhood is influenced by vast structures beyond, linking the Milky Way's fate to the larger-scale architecture of the universe. In summary, the Milky Way resides in a vibrant, interactive neighborhood within the local group. It is a dominant galaxy, surrounded by numerous satellites, interacting with smaller dwarf galaxies, and slowly approaching its giant neighbor Andromeda. These interactions have shaped the galaxy's halo, warped disk, and streams of stars, and will continue to mold its structure in the billions of years to come. Understanding the Milky Way's neighborhood provides critical insight into its past, present, and future, situating our galaxy not as a solitary island but as a participant in a dynamic cosmic ecosystem. The Milky Way's story is far from static. While it has grown over billions of years by accreting smaller galaxies and forming stars within its spiral arms, its future is poised for one of the most dramatic events imaginable, a collision with the Andromeda Galaxy. This event, predicted to occur in roughly 4 billion years, will fundamentally reshape both galaxies, creating a new, merged system and offering a spectacular glimpse into the long-term evolution of galaxies in the universe. Currently, the Milky Way and Andromeda are on a collision course, approaching each other at about 110 kilometers per second. While the distance between the two giants is immense, approximately 2.5 million light-years, gravitational attraction ensures that they are inexorably drawn together. Over billions of years, their mutual pull will overcome cosmic expansion in their local region, and the two spiral galaxies will begin a slow, complex dance. This process will unfold over several billion years, not as a sudden crash, but as a series of close encounters, tidal interactions, and mergers of stars, gas, and dark matter. As the galaxies approach, their mutual gravitational forces will distort their shapes. Tidal forces will stretch the Milky Way's and Andromeda's disks, creating long streams of stars and gas known as tidal tails. The spiral arms will become elongated and twisted, and the outer regions of each galaxy will be pulled into intricate patterns. These interactions will trigger bursts of star formation, as colliding clouds of gas compress and collapse under gravity, producing new generations of stars at rates far higher than in either galaxy's current quiescent state. Star clusters and nebulae will light up the merging systems, creating a spectacular cosmic fireworks display. Despite the grandeur of the event, the stars themselves are unlikely to collide directly. Stars are incredibly small relative to the distances between them, so while the galaxies will pass through each other and eventually merge, most individual stars will sail past one another unharmed. However, the orbits of stars throughout both galaxies will be dramatically altered. The Milky Way sun, for example, may find itself flung into a new trajectory, possibly far from its current location in the Orion Arm. The familiar night sky would be unrecognizable, with countless new stars visible as the galactic structures intertwine. The dark matter halos of the Milky Way and Andromeda will play a critical role during the merger. These halos dominate the gravitational potential of each galaxy, dictating the paths of stars, gas, and satellite galaxies. As the halos interpenetrate, dynamical friction will slow the motion of the galactic cores, causing them to spiral closer until the supermassive black holes at their centers eventually coalesce. This merger may release gravitational waves, ripples in the fabric of space-time, detectable across the cosmos, marking one of the universe's most energetic events. Over the course of several billion years, the collision will transform the structure of both galaxies. Spiral arms will be disrupted, disks may be thickened or destroyed, and a more spheroidal shape will emerge. Simulations suggest that the resulting system will resemble a giant elliptical galaxy or a lenticular galaxy, with a dense central bulge and a less pronounced disk. Star formation may gradually decline after the initial burst, as gas is consumed or expelled, leaving behind a more quiescent galaxy dominated by older stars. This cosmic merger is not unique to the Milky Way and Andromeda. Galaxy collisions are common in the universe. In fact, our own galaxy bears the scars of past mergers. Streams of stars in the halo, remnants of accreted dwarf galaxies like the Sagittarius dwarf, are evidence that the Milky Way has grown through collisions before. The impending Andromeda encounter is simply on a much larger scale, involving two massive spiral galaxies rather than small satellites. Interestingly, the timing of the collision means that humanity's long-term descendants, if they still exist, may witness, or at least be in the aftermath of, this galactic transformation. For our current solar system, while the local gravitational environment will change, the vast distances between stars mean that direct encounters are improbable. However, our position in the merged galaxy will likely be very different, possibly in a new orbit far from the galactic center or near a newly formed stellar cluster. The collision with Andromeda also has implications for the local group. After the merger, the resulting galaxy will dominate the group, absorbing smaller satellite galaxies and possibly interacting with Triangulum in the future. The dynamics of the local group will be altered, with tidal forces, gravitational perturbations, and halo interactions reshaping the orbits of remaining satellites. In essence, the Milky Way's identity as a separate spiral galaxy will end, replaced by a new, massive, and complex galactic entity. Ultimately, the predicted collision is a reminder that galaxies are dynamic, evolving systems, not fixed structures. The Milky Way has been shaped by past mergers, will continue to evolve through ongoing accretion, and will experience one of the most dramatic transformations in its future. This event underscores the immense timescales over which galactic evolution occurs and offers a glimpse of the cosmic processes that govern the universe at the largest scales. In short, the future collision with Andromeda is set to radically reshape the Milky Way, transforming its spiral structure into a massive elliptical or lenticular galaxy, altering stellar orbits, igniting bursts of star formation, and permanently changing the architecture of our cosmic neighborhood. It is a vivid reminder that the galaxy we inhabit is a transient stage in a story billions of years in the making, where gravity, dark matter, and cosmic time sculpt the universe itself. Standing back from all the details, the stars, the spiral arms, the halo, and the dark matter that binds it all, we finally reach a point of profound perspective. The Milky Way, with its 100,000 to 120,000 light-year disk, its hundreds of billions of stars, its sprawling halo of dark matter, and the supermassive black hole at its center, is a structure of staggering complexity and scale. We now know not just its dimensions, but also the dynamism hidden in its warps, streams, and tidal ripples. We can trace its spiral arms, understand its rotation, and predict its eventual fate as it collides with Andromeda. For humanity, this is a monumental achievement. After centuries of curiosity, observation, and the development of revolutionary technologies, the veil has been lifted on our galactic home. Yet even as we marvel at its immensity, it's essential to place the Milky Way in its cosmic context. Our galaxy is but one among trillions scattered throughout the observable universe. Galaxies come in countless forms: giant ellipticals dwarfing the Milky Way, dwarf irregulars barely containing a few million stars, massive spiral galaxies with majestic arms rivaling our own. Each galaxy is a universe in miniature, with its own intricate dance of stars, gas, dust, and dark matter. And while the Milky Way is dominant within the local group, it is only a tiny participant in the vast cosmic web, bound with other galaxies into clusters, superclusters, and filaments spanning hundreds of millions of light-years. This perspective is both humbling and exhilarating. From our vantage point inside the Orion Arm, it is easy to forget that the Milky Way itself is just one luminous island amid a cosmic ocean. Even with all our technological advances, radio telescopes, infrared observatories, and space missions like Gaia, our view is limited. We cannot step outside the galaxy to admire it as a whole. We must reconstruct it from within, using careful measurements, clever modeling, and patient observation. That effort has revealed a galaxy of astonishing scale, beauty, and complexity. But the universe itself stretches far beyond our comprehension. The Milky Way's story of formation and evolution mirrors the grand processes at work in the cosmos. It was built from smaller galaxies, shaped by gravity, dark matter, and cosmic interactions, and it will continue to change, ultimately merging with Andromeda in a dramatic, galaxy-wide transformation. Its stars trace not just the history of our own neighborhood, but the echoes of countless accreted systems, interstellar collisions, and the slow, invisible influence of dark matter. By studying it, we glimpse the forces that govern the universe, from the smallest scales of star formation to the largest scales of galactic mergers and dark matter dynamics. Even as we acknowledge the Milky Way's immensity, we are reminded that the cosmic scale is even more astonishing. Each star in our galaxy may host planets, some of which could harbor life. Each galaxy in the universe contains billions or trillions of stars, and countless galaxies are yet to be discovered beyond the observable horizon. Our galaxy is both familiar and mysterious. It is our home, yet it is vast beyond imagination, with regions we may never fully explore, structures whose dynamics unfold over hundreds of millions of years, and dark matter shaping it invisibly. The awe deepens when we consider time alongside space. The Milky Way is about 13.6 billion years old, nearly as old as the universe itself. Light from its most distant stars takes tens of thousands of years to reach us. Its rotation, spiral patterns, and warps evolve over millions of years. The galaxy is alive in a sense that human lifetimes can barely perceive, yet we have begun to chart its motions, understand its structure, and predict its future. Our existence, our observations, and even our understanding are fleeting moments against this backdrop of immense cosmic time and space. In the end, the story of the Milky Way is a story of discovery, perspective, and humility. We have mapped its spiral arms, measured the mass of its stars and dark matter, and located the solar system in the Orion Arm. We know the supermassive black hole at its heart, the streams of stars from devoured dwarf galaxies, and the distant future in which it will merge with Andromeda. And yet, as vast as it is, the Milky Way remains only one galaxy among countless others, a luminous thread in the cosmic tapestry. This perspective reshapes how we think about our place in the universe. The Milky Way is enormous, majestic, and teeming with complexity, but it is also a single chapter in an infinite cosmic story. Every star we see in the night sky, every spiral arm traced through radio or optical observations, every distant halo stream, is part of a galaxy whose story intersects with billions of others across the universe. By understanding our galaxy, we glimpse the nature of the universe itself, its immensity, its dynamism, and its boundless potential for discovery. In the quiet of a starry night, when the Milky Way stretches across the sky as a luminous river of stars, we can reflect on the remarkable journey of humanity's understanding. From early astronomers peering through crude telescopes to modern missions charting billions of stars, we have unveiled the scale and structure of our home galaxy. And yet, even with all this knowledge, there remains an almost unimaginable vastness beyond, a universe where the Milky Way is just one of countless galaxies, each with its own mysteries waiting to be uncovered. In that realization lies both humility and inspiration. We live in a galaxy vast beyond comprehension, orbiting in a modest spiral arm, witnessing only a tiny fraction of its structure directly. At the same time, our ability to understand it at all, through mathematics, observation, and imagination, is a triumph of curiosity and intellect. The Milky Way is a testament to the complexity of the cosmos, a laboratory for the forces of nature, and a reminder that even in the vastness of the universe, we are capable of uncovering its deepest secrets. The Milky Way story, from its sprawling spiral arms to its hidden dark matter halo, its stellar streams, warped edges, and future collision with Andromeda, is the story of scale, motion, and cosmic evolution. And as we step back from its brilliance, we see it not as a singular marvel, but as part of an endless cosmic ocean, where each galaxy, each star, and each planet is a thread in a tapestry whose richness and complexity exceed even our wildest imagination. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.